Today's topic is covered around recipient Barbara Liskov. And then we have a tea break, and then we follow that up with a panel discussion. So before we get started with today's event, let me quickly give a summary of why we started doing this. As you all know, last year was Alan Turing's birth centenary, and so we said, let's do something to commemorate that event. Alan Turing, as you all know, is considered as the father of computer science, and he's also well known for his as a mathematician, as a logician, as a cryptanalyst, as well as a long-distance runner. So we started last year with having these technical talks for every month, and thanks to the support from the audience and the interest that was shown, we decided to continue these talks beyond the 1 year as well. So that's why we are in this year 2 of this Tech Talk series. One of the things we found that we have been finding is that though he is considered as the father of computer science and we are all in this domain, his contributions are not well known. So the idea of these talks is to basically cover his contribution as well as contributions made by various Turing Award recipients. So every last Saturday of every month, starting from July, we have been doing this. We'll continue to do this. Take one Turing Award recipient and have an expert talk about the contributions, followed by some related talk, panel discussion, whatever, to bring out some of the nuances of that contribution. Okay, the details are available on our website, so feel free to go browse. All the technical talks, the videos, the presentations are all available from that same site. So please go. If you've missed any of those events, previous talks, please visit the site to get and watch the video, watch the presentation, so that you get an idea of what was covered in that during that event. So today's Tech Talk will be contributions made by Barbara Liskov. She has made immense contributions to practical and theoretical foundations of programming languages and system design, especially related to data abstraction, fault tolerance, and distributed computing. And the speaker for today is Ajay Deshpande, Chief Architect at Persistent Systems. All these talks are under the auspices of the ACM technical body, and a lot of details about these Turing Award recipients can be viewed at the ACM's website, amturing.acm.org. And of course, our website also has all the details about the events that we have conducted in the past and the upcoming events as well. So without further delay, let me welcome Ajay Deshpande, Chief Architect at Persistent Systems, to take the stage and talk about the contributions made by Barbara Liskov. Ajay?
Thanks, Anki. First of all, good afternoon, everyone. My name is Ajay Deshpande. For people who do not know me, I work for Persistent as a software architect. And what that means is designing software, thinking about how software is built ground up, and thinking about how to organize software. So that's what a software architect does, pretty much like a growth of extension of a software developer, so to speak. Today I will be talking about one of the greatest ladies I've ever known. From whatever I have been reading so far, after this research about Barbara that I did, I realized there is such a personality that we should all know about. So this was a very interesting opportunity that I got to understand more about Barbara and see what she has done. So as I went through all this research, what I realized was that this lady has contributed to things that we do as programmers day in and day out. So it's a very interesting thing that we have been using so many things in programming languages and distributed systems without ever knowing who was behind it. And it so turns out that Barbara was behind a lot of things that we have taken for granted. So that made my job a lot easier, because whatever I'll be talking about, kind of every programmer would know one way or the other. So let's look at what is Barbara's career highlights. So if you look at these things, currently she is a professor she's an institute professor. That's a special kind of this thing that MIT gives. She's been there for a long time. She works at the computer science and artificial intelligence lab. She is also head of a group called Programming Methodology Group. She got the Turing Award in 2008. The Turing Award was given for her contributions to programming languages, which we'll see. Kind of came a little late, as I would say, but nonetheless, she got it in 2008. She also has these other bunch of awards to her names. It's just a few of them that the slide could only hold a few. But if you look at her resume is 37 pages long, and 2 pages are awards, about 20 pages are publications. So if you look at the right side of the slide, if you look the contributions that she has given, so more than 130 research papers which are published. So that's a phenomenal amount of work that she has done. She has guided 25 PhD students. If you look at her career, it's been about 40 to 45 years in computer science, in which she has 25 PhD students under her, which means like she's been churning out a PhD every 2 years or so. 75 master's dissertations. So again, like it's like a phenomenal personality that we are looking at. So there is a lot of interesting thing beyond this personality. One of the first things that strikes is she got rejected for a PG course by Princeton because Princeton said that we don't admit ladies. So that happened in 1961, and as you can imagine, 1961 was a time when women were not in the forefront. The women's lib had not yet happened and things like that. So what would one expect to do is, they did not accept me, so let me go back and do a secretarial job or something like that. That was not what Barbara did. She went into a company called Mitre, which helped her to hone her skills in computer science. And eventually she landed up in a PhD program, the first ever PhD program in Stanford, and finished that in 1968. As we will go, after I go through the technical content of her work, I'll also talk about this personality a little bit more, interesting things about her. Some of the ideas that she has laid as the foundations, if you look at programming languages, if you look at distributed systems, if you look at fault tolerance and security, all of these are seminal contributions in the sense that we use a lot of these today. Like I said, we take these things for granted. So it so happened that everyone supported her Turing Award given to her, but interestingly, every major person had a different branch of science in which she should be given a Turing Award. So the kinds of contributions she has done are span many branches of CS. So it's a kind of an interesting thing about her. So let me give you a quick highlight of the career, or a little bit more about the career. Like I said, she finished her mathematics BA in 1961, when she tried a PG program in Princeton, which she did not get, which actually was a good thing, I think, in hindsight, because she did not get into Princeton, she got into Mitre, and she converted from a mathematics student to a computer science student. So when she was in Mitre, she realized that she needs to do a lot of learning in terms of computer science. So that's when she went back to Stanford and finished her PhD in 68. She came back to Mitre, but this time she was a research assistant rather than a software programmer. So as a research assistant, she went into developing what was called as Venus operating system at that time. So again, it was around the times when Unix, Multics, Ultrix, all of these were being developed from scratch. So she did Venus operating system, and then in 1972, one of the heads of computer department in MIT convinced her to start a career in teaching. So that's when she went into MIT, and she's been in MIT since 1972. And here is what she did in MIT. 1970s, when she first started out there, she started with, when she did a lot of these programming things, she realized that programming was very haphazard at that point of time. That's when she came up with all her guidelines, principles in how we should be programming. She invented a language called CLU, which kind of demonstrated what she was teaching in theory. In the 1980s, she turned her attention from programming languages to distributed systems. Into distributed systems, she started doing a lot of work around trying to build systems that are resilient, systems that can recover from system crashes and things like that. So there are a lot of interesting protocols and stuff like that we'll be talking about that she has contributed to. And after 2000s, in and around 2000, she started working in security and fault tolerance in high-end distributed systems, privacy of information. And in 2013, she submitted a paper that got published in privacy of data on internet systems. So a person of this stature, she's been contributing papers regularly, contributing research from 1970s to even 2013. So that's the personality we are talking about today. Let's look at her important contributions. This is a kind of a laundry list of things I just wanted to say. I'm not going to delve into each of these. I'll pick some of these important ones which are relevant to us as software programmers, which we will talk about. But to start with, her first thing that she contributed as a software was a program that did chess end games. That her PhD is in that. So she built a system that could play good chess end games. Then she started working on abstract data types in programming. We'll talk about that. Then she also did a lot of interesting things around how should subtyping work or inheritance in object-oriented systems work. So she did a lot of work on that. She told the world that modular programming is the right way to go, is the right way to show that your programs are correct. So she did a lot of work around modular programming. Remember, this was the time when people were throwing go-tos into their programming all over the world, because when people transitioned from assembly, the way assembly programming was done was that we didn't have loops and all. We used to use go-tos and jump ifs kind of thing, right? So all of that came into the high-level languages, and somebody needed to get in. There is Dijkstra, there is Hoare, there is Knuth, who all came up with modular programming. Barbara was one of them who contributed to that whole movement, so to speak. She also has contributed in the 1990s on structured exception handling, which not many people had contributed earlier in. So exception handling has now become like the norm in most of our high-level programming languages. So she laid the foundation to that as well. Let's look at distributed computing, what she has contributed in. First of all, she's developed a system that we will look at that she called as Argus, which was a system plus language to develop distributed computing systems. She has algorithms that are patented in garbage collection in distributed environments. Then she also did object-oriented distributed system. They called it Thor. So natural extension to having a distributed system to build an object-oriented database that runs on multiple distributed. Then she also built some these things in peer-to-peer networks. Again, look at the kind of she was in distributed systems, moved onto peer-to-peer kind of systems. She has papers again in building robust services in dynamic systems. Dynamic systems are basically, if you have like a mobile kind of situation, a mobile is occasionally connected. So those are dynamic systems. So she has papers in those areas as well. So as you can see, a lot of work again in distributed computing. Then in security, she has primarily contributed to replication as a mechanism to save data or protect data. So when data is stored at one system, it can be replicated and hence data is protected so that because of crashes, you don't lose data. So that is a very key point that she has added to. Of recent times, she has published papers in rendering malicious clients harmless in a large system. So how can we make sure that whatever a client does is tracked and labeled as malicious, and then you kind of move it out of the system. So there's a paper in that. So like I said, the last one is protecting privacy in internet systems like Facebook and those kind of systems today. So her research is in this area today. So as you see, there is a vast range of things that she has done. So what I wanted to do was talk about 2 or 3 things in this hour or so. So the first thing I wanted to talk about is programming, because programming is so near and dear to all of us. So programming is one. And then the other one I wanted to talk about is distributed systems. So I'm not going to cover everything that she has done. I just gave a high-level idea of that. So in programming, let's start with what was called as programming with abstractions. So again, like I said, this was the 1970s, and people were programming haphazardly, to say the best. In the sense that they had moved from low-level languages to high-level languages, and people were still discovering how to program. She worked with Steve in this picture here, and built up this whole kind of infrastructure around programming, how to program, and what is the right thing to do and what is not. So the first one, if you look at this, is what they together called as abstractions. And we are all very kind of well acquainted with abstractions. Abstractions is a way of exposing the right things while not exposing the things that are not necessary for a customer or a client of a system to know. So if you look at, we talk about interfaces today. Right? Interfaces is nothing but is a way of abstracting things. So what you are doing is you are trying to expose what the system does, what a person can expect from the system. Right? So that is an abstraction. There are multiple kinds of abstractions. Okay? The first is what we call as functional abstraction. So basically, we take a bunch of code and put it into a function. And our intention of putting it into a function is that I don't want to expose how I'm computing the algorithms and things like that internally. All I'm going to say is that this function does a sort job. Okay? So the sort job is expressed by taking a list of things, maybe a comparison function, as the inputs, and it gives you a sorted list of things as output. So that is the interface to your sort function. So that is functional abstraction. I don't tell you how I'm going to implement the sorting within. So that is functional abstraction. Then we are aware of data abstraction. Basically, when data is represented I can abstract it out. I tell you that this is a linked list. Don't worry about whether I'm using an array to implement a linked list or I'm using a set of pointers based mechanism to implement a linked list. So the data abstraction is a way of either composing things together or aggregating things together and building more complex data types out of simple ones. Then we also have control abstraction. Okay, control abstraction is about how do I expose new ways of computing. So for example, thread is a good control abstraction. We did not have threads earlier, but of recent past, threads are very common. So thread is a way of abstracting control. That is, there's a control flow, and it can be started, it can be stopped. Similarly, transaction is another notion of control abstraction. Either a transaction completes fully or it does not complete. Right? So it's an atomic operation. So these are various abstractions, and the word abstraction in programming was introduced by Steve and Barbara. And that kind of brought programming to a much higher level than what was known until then. They further went ahead and defined what is called as an abstract data type, which is what we know of as interface today or a class. So basically an abstract data type is characterized by the operations that can be done on the data type. Okay. So if you look at, for example, our popular data structure that we know of, a queue, let's say, a queue has a bunch of operations that you can do on it, and that's how you know of a queue. So a queue is an abstract data type which is characterized by the operations that can be done on it. So these data types, when written in a program, they become first-class citizens. So what do I mean by first-class citizens? They have the same amount of, if you want to call it flexibility, or same amount of recognition as a basic data type. What that means is I can actually call operations on it. I can define new operations on this data type. So the language should allow me to define operations on this data types. So this is what is meant by an abstract data type. And when Steve and Barbara defined it, they had a concept of something called as cluster. So a cluster was basically what we would call today as a class, basically data and operations on the data put together. So this is an abstract data type. To prove to the world that this is how programming should be done, to show to the world, what she did was that she went ahead and defined this new language. It's even available today. You can download the compiler, you can download stuff. It's called as Clue, and it's available from MIT's website. Clue stands for cluster, the first three words of cluster. So their primary key of Clue was it had clusters. It had polymorphism, it had exceptions, and it had iterators. Again, all of this we take for granted today, right? All of these things are there in most major modern languages. But think of these in 1970s. So that's where Barbara's contribution becomes so much more important. It was a heap-based language. Again, most of our languages today are commonly heap-based languages. Has a garbage collection. It became the predecessor, obviously, to all modern languages. What she showed of all this using Clue and the abstraction definitions is that programs written in this way are easier to maintain. Okay, are also easier to prove that they are correct. And that is the key point, and they have treated this mathematically. That's very important. In addition to having also things like the actual compilers and environments to program and all that, they also have treated this mathematically and actually shown that these are more modular. They have come up with a nice infrastructure of what does modularity mean, what does maintainability mean, things like that. So this was a very important thing because it paved things like packages, what we have in Java today, or namespaces in C#. All of these kind of, in one way or the other, all these languages kind of date back to this time. The next one that is interesting in this area is what is called as type hierarchy. At that time, again, object-oriented programming was kind of coming into force just about there. So people were still experimenting with how to inherit from this thing. For example, is multiple inheritance good, or should it be single inheritance? Similarly, there is also a concept called inheritance for implementation. What that meant was that I had one class, I would inherit from that class because I didn't want to rewrite that code again. And beyond that, there was nothing common in these two classes. So, which was a stupid way of doing inheritance, and it didn't fly too much, but basically because it violated encapsulation, like she says in one of her papers. So implementation inheritance was done away with. So what Liskov did was that she came up with this very interesting principle, which sounds common sense when we understand what it is. It's called as Liskov substitution principle. So what it basically says is that when you have inheritance, the objects of the subtype, that is the one that is inherited from the parent, the objects of this type should behave like the supertype. Okay, should behave, that's the interesting thing. Behave like the supertype when you are called via the supertype interface. So let's say, for example, a simple example here is I have a person and maybe a teacher. So teacher is a person. So teacher is a subtype and we have person. So if person has a get age, okay, method on it, then I would expect the teacher.getAge should also behave exactly same like what the person.getAge does. Now this is common sense, right? But interestingly, this had to be published as a principle to tell people that this is how you should design programs. So basically what it implies is that the subtypes should not change the semantics of the supertypes for the interface that is the supertype. The subtype might be implementing other things as well, for which there is no, this does not apply obviously. But for the interface that is for the supertype, it should not change the semantics. Now this looks very, like I said, common sense, but it has been the cornerstone for object-oriented design for all these days. So anytime it's actually more than just the language thing. It's more of a discipline. It's more of how to program. So she's telling us how you should be programming correctly. So here are a couple of examples. Let's say I inherit a square from a rectangle, because finally a square is also a specialized rectangle, right, where length is equal to breadth. So is this a good inheritance? So according to Liskov's principle, substitution principle, this is not a good inheritance. Although it might sound reasonable at one point, this is not a sound, this is not a, it violates LSP basically. So why does it violate? Because when I look at a rectangle, I have this implicit notion that length and breadth are unequal, and so I might have something like set length, set breadth, compute area, things like that, right? So what happens is that when I say if I have a square which is inherited from rectangle, and I say square dot set length, then what happens? Internally it will also go and set the breadth, right? Because length is equal to breadth, right? Which is kind of violating the LSP, because the semantics is different. Although in reality it might sound like it's a nice way to inherit, right? Another example I have here is you're trying to inherit a stack from a bag. So bag has put and get methods on it. So what I will do is I will use put as push for stack and get as pop for stack. Now again, this violates LSP because the semantics is very different, as we can understand. So if I use the bag in place of a stack at places, then what will happen? If you try to do something where you expect a stack is working, obviously it will not work, right? So this was something that she published and again came up with some interesting research infrastructure around this, and this has become, like I said, common knowledge. And interestingly, this is what got her the Turing Award. So as you can see, we'll see a lot of other interesting things she has done, but finally the Turing community kind of chose, okay, this seems to be the biggest contribution, most far-reaching contribution from her, and that's where she got the Turing Award. So that kind of brings us to the brief this thing about programming with abstractions. Okay. What we will do now is jump into distributed systems. At this point, I'll just pause for a second to see if there are any questions. So we can always have questions in the end, but if you have questions, we could also discuss as we go along. Yes, please. There is a question. Yeah, go ahead.
Okay. So the question is, the LSP tells us not to kind of override the base classes behavior, but the polymorphism says we can override that behavior as well. So so clue, for example, has both the things. So doesn't that is?
Yeah, very interesting. I was hoping somebody would ask that question, so it's good. So the question is, we are saying that LSP says don't override, while polymorphism means override. It implies that it's overriding, right? So that's a good point. So, like I said, let's go back to that example that I was talking about earlier, which is the person and a teacher. So get age is what we are talking about here, right? So if you look at get age, for the person, we might be computing it as date of birth or current date minus date of birth. Okay, that could be get age. But for the teacher, we might compute it as in some other way. This is just a fictitious way of computing. I'm saying number of years of experience, number of years in the college, plus number of years in high school, let's say. So this is how I am computing age for this. Now I have overridden here, okay, but I have not changed the semantics. You see what I'm saying? So overriding does not mean that you change the semantics. So the point about LSP is that you should not change the semantics of the. So get age should not give you salary, for example. That's what she says. Okay. So but polymorphism is important, and polymorphism exists in many different ways. Like we are saying, you can introduce the same function doing different things differently, or it could also have multiple other members, which makes it behave differently. So polymorphism does exist. So it's a very good question. Yeah. Please.
Is it safe to say that the object-oriented languages like C++ was developed upon the concepts of data abstraction provided by Ms. Liskov?
Yes, the question is it safe to say that object-oriented languages were constructed on abstraction defined by Liskov? I would say an emphatic yes. Not only C++, but all object-oriented languages. In fact, the object-oriented paradigm that we think, paradigm is the way of thinking, right? That itself is very much coming from Barbara's work. So it's definitely true. Okay, so what we'll do is we will delve into distributed systems now. The first one I will talk about is what she called as HARP, HARP stands for highly available, reliable, persistent file system. So again, this was invented around 1980s kind of thing. And if you look at the situation then, situation was that people were trying to have stable storage. First of all, the storage was not large, number one. Second was that the disks were not so good in quality, in the sense that they would crash. And third, if you needed all of these things, a fast disk, large volume, and also good quality, as in it doesn't crash within a given time, means you would spend a lot. Okay, so if you needed these good qualities, then you would spend a lot. So the problem that Liskov was trying to solve here was that without spending a ton of money, can I get all these good qualities? Okay, so that is the idea that we are trying to solve here. So the HARP file system was that. What they did was that they provided it as an NFS file system, which means it's a network attached, storage, which could be put on any network thing, and any computer could mount this file system onto their thing and use it as a local file. Then you can write to this, read from the file system. So that's how how it was provided. What they tried to provide was that it was to be available in spite of hardware and software crashes. Even if this file server had different components, things would crash, it would still be available. That's what they were trying to do. File operations were atomic. So if I write 10 bytes to a file, all the 10 bytes get written or nothing gets written. Right? And then an operation either completes successfully or, like saying, atomic. And then it was all built on conventional hardware, which was the key point about HARP. So it was built on cheap conventional hardware. So to provide all of this, what she did was that it implements something called as primary copy replication mechanism. So a primary copy replication mechanism is basically you have a primary copy of the file, okay, and then there are multiple backup copies. So you write to the primary copy, and the system takes care of making sure that the other copies are consistent with this copy. That's what this technique is about. So we'll get into that in a little bit. A couple of other interesting things about these features. So there are some assumptions that they were making. No message corruption, which means that the network wouldn't deliver half-baked messages or messages which are mutilated. Nodes are loosely synchronized in time. Okay, and then servers have a UPS to handle power failures. So one of the things was that if there is a power failure, UPS would kick in and it would save some state. It will get enough time to save some state to disk. So at least it won't lose your updates. And then it is built on a fast network. At that time, they used to have 100 Mbps kind of. It was a kind of fast network. The kinds of failures they tried to work against is hardware crashes, then software crashes. Message loss was okay. They would try to recover from message loss. Then messages arriving out of order was also okay. So they would again take care of that. And finally, network partitions. So if you have like 100 servers working together as a file system, if 25 of them get partitioned as a separate network, then it would still work. Once they join back to the partition, they would all come back to a consistent state again. So the innovative thing about this particular mechanism was that the updates, when you write to the primary copy makes a log entry for it, saying this is the update that is coming in, like something like previous value and new value kind of thing. It saves that entry in main memory, does not write it to disk, but it writes to other neighboring nodes and their main memory. Okay, and then it would respond to the client saying success. So interestingly, the disk writing was removed from the critical path of updating a record. The writing to disk was removed from the critical path. So which was a very novel idea at that point of time. So, and they still guaranteed consistency. So that's the interesting thing about this. The actual writing to disk would happen in the background. So that's how it would work. So we'll talk about the system architecture in a bit. I have a diagram on that. But there are three kinds of nodes in this whole system. There is a primary node. The primary is the node which manages the file, let's say. And then there are backup nodes and there are witnesses, okay, which participate in the protocol of making consistency happen. Okay. All of this together is called as a view, the view of the system. So view consists of this is my primary, these are my backups, and these are the witnesses. Okay. So that's the view of the system. I depict that in this diagram here. So if you look at this diagram, there is a primary on top which interacts with the NFS clients. So the NFS clients would send update requests, read requests, whatever to the primary. Okay. And there is always one primary. And then there are backups, n backups and n witnesses. So I have shown them, there is a bit of color coding there if you look at that. So the dark brown, the big brown part is actual file system. Okay. And the small brown part is the log that is contained, which is maintained for updates coming in for the file system. Right? So what it shows is that the witnesses do not contain the complete file system. Okay. And witnesses contain only the logs as necessary. So when we look at the algorithm, we'll get to that. So as I said, the primary gets an update. It takes the update, makes an entry into the log, sends it to the backups. Okay, they make their entries into their logs and then respond to the primary. And primary says success without going to the disk. This is the primary mechanism, how updates happen. So we'll talk about that in a little bit. So all of this together is called as a HARP view. Yeah. Yeah, witnesses also can listen to the logs and get them. So they can be sent. We'll come to the algorithm in a bit. So they will get logs when necessary, when there is a crash, to handle crashes, basically. So that's an interesting setup here. Now, if we have this kind of a setup, this will help us recover from n crashes. So I have 2n plus 1 servers. It will help me to recover from n crashes, which means, for example, if I have 3 servers, okay, which are working in this mode, one primary, one backup, and one witness, that means I'll be able to recover from one crash. Any of these machines crashing, I'll be able to recover from that. Okay, so that's the model. So if you want recovery from n crashes, then I would need 2n plus 1 servers, which is like normal for most replication kind of algorithms. Now what happens inside every server? So inside every server, the architecture is like this. So there is the server code, okay, which implements the NFS interface. The NFS then underneath talks to a VFS interface. VFS is a virtual file system interface. So this is like a standard for file systems. So you can implement VFS, then you can talk to a Unix file system or you can talk to some other file system, does not matter. So the VFS is kind of an insulating layer that can be used. So not necessary to be used, but they were using this. The VFS then internally talked to the Unix file system and the HARP file system interface. The HARP was the one which talked to the network and got these things going. Okay? So this is the overall architecture for HARP. Now let's look at what happens to the updates. So we will look at 2 scenarios. One is the update scenario, what happens when update comes in, and another scenario where we are going to talk about recovery when there is a crash and it comes back up, right? So when the update comes in, like I said, primary manages a 2-phase commit kind of situation. So it first makes its own log update, and then it is going to send it to the others. So now each server here maintains that event log that I was talking about, which is basically coming in as a set of entries, updates to the file system. So the primary sends the log entry to the backups and they respond. Once they all respond, then the primary responds to the NFS client saying your update is done. That is, it is committed. So they have a concept of a commit pointer into this log. So we'll come to that in a bit. So the interesting thing is all data writing to the disk happens asynchronously. Okay, all of this data that goes to the disk is happening asynchronously. Now let's look at this log entry. This is how the log would be looking like. So the log is basically a long running set of records. So at the top you see new entries are being made. That is, these are the requests from NFS clients. And then at the bottom, we will discard the entries as they are successfully, they have made it to disk. Okay, this is how the log looks like. These are the log records. Now the first interesting point that I was talking about was the commit pointer. That is at the top of, next to the log top. So the commit pointer is last committed record on my view. That is this is my system, right? So the commit point basically tells that I have sent a message to all backups and they have responded, and I have sent back a response to the NFS client saying that this is committed. So that is what that pointer tells us. Then applied point and lower bound, these two are basically points which tell us about, applied point basically says here is the IO for this has started, maybe it's in progress being written, and lower bound is IO is completed. Okay, so the lower bound, all records below the lower bound is that all these records have made to disk. Okay, and LB, that is the lower bound, stands for my disk. This is on one server, right? What we are seeing here. This is for one server. This is my disk. So now we have this whole bunch of backups and primary together, right? Now the idea is that to move all these pointers along when all of them write to their disk. So the global lower bound is that pointer. Okay. So the global lower bound is the pointer of the slowest system that is writing to disk. Make sense? So again, the commit pointer is what has been responded to the NFS client saying this is committed. So all of them now have this log entry, everybody participating in this system. The applied point and lower bound, those 2 points, AP and LB. AP is IO for this has been started, will be writing to disk, and LB says that IO for this has been completed. And LB says my local pointer. And GLB is the global lower bound, which is all these guys together. Everything has been written to disk. Yeah. No, it will be same across all of them. Meaning there might be delays in network delays, but basically the idea is that all backups, when they are responding, this is all this information is piggybacked on messages and broadcast. So everybody can get it, but they can be out of sync because of message delays or not getting messages. So now the algorithm, basically what it is trying to do is that this is the state that is maintained across this distributed system. So we need to take all these 4 pointers up, move them up as it goes along, and make sure that when things crash, then we all get this information, reconstruct this information somehow from the other servers. That is the idea here. Okay. So let's see what happens in a system crash, right? For understanding what happens in the system crash, we all need to appreciate this invariant, that is the GLB can never go beyond LB. and so on and so forth. That invariant holds all the time. So let's look at what happens in crash recovery in HARP. So the first thing we need to understand is in a crash recovery, there are 4 scenarios that we need, 4 dimensions, so to speak, that we need to take care of. So the 4 dimensions are correctness, in the sense that the commit order is maintained. So if, let's say, the NFS clients have asked for 10 operations and I get back 10 responses saying success in some order, that order needs to be maintained. Okay. So basically what they say is I wrote this file first and then this file and then this file, right? And this record and this record, that needs to be maintained. That is correctness. The second one is reliability. Reliability means once an operation is committed, it is available forever. So it cannot be lost because you had a system crash or you had something going wrong. Right? So that is the second one. The third one is availability. Now this is an interesting point. So not many people look at this way. But basically we have 2 n+1 servers. Suppose 10 of them crash, the system should still function in whatever proportionally reduced kind of functionality. The speed might go down or whatever, but it's still available. That's an important point. And then timeliness. So if there is a crash and it takes hours and hours to come back to live, that's not acceptable. So timeliness measures that parameter. So here is what happens when a server restarts. It crashes and comes back up. Okay. So what would happen here is that it communicates with a member of the system, okay, and asks for what has happened when I was not there. So how can this be identified? So the state that we had in this thing, that can tell us what is there on my file system and what is not on my file system. So that can be used to this thing. So what it does is that without bringing anything else down, it has come back, it just sucks in information to come up to speed. Okay, so nothing else changes, but it's just trying to catch up. So once it catches up, then it does what is called as a view change. Okay, now I'm saying the server restarts, the server could be a primary that had crashed, or it could be one of the backups that had crashed. Right? So it then does what is called as a view change. So the view change is a 2-step process. It's basically a 2-phase commit kind of process, which tries to get the system back into a sync state. Okay, and then again identify who is the primary and who are the backups and get them back to speed. That's the goal of a view change process. So usually the view change process is started by the primary. Okay, so why start from a primary? Because basically the idea is that if there are multiple view changes going on simultaneously, that's not acceptable. We are trying to recompute a lot of data. So the primary always starts. If primary is alive, it's the primary which starts the view change process. Okay. If primary is dead and that has the one that has crashed, then one of the backups will start the view change process. Okay, so which means they will find a new primary. So now what happens is that the system is configured with you are the designated primary, you are the second designated primary, and so on. Okay, so there is a hierarchy of nodes introduced, which is static information, and that's how the next primary will be chosen if the primary crashes. Okay. Like I said, the last point, algorithm ensures that there is only one view change in progress at a time. So what happens in a view change? Let's look at this a little bit carefully. So in the phase 1, first of all, the primary which has started this view change gets a kind of a vote from everyone saying, I have started the view change process. If it does not get any votes, then it knows that that node is down. So it knows there are certain other things that it needs to take action on. The other important thing about view change process is this is where the NFS requests are stopped. Meaning when a system is going through a view change setup, the new NFS requests are blocked. Okay, that is the system is not available. So once this coordinator gets all the data and it's up to date, it removes the nodes that did not respond from this view. So it basically a view is the new configuration of the system, right? So then in the new configuration, there will be some nodes that might be removed and some nodes that will be included. This is where the secondary nodes, that is what we called as witnesses, come into picture. Yeah.
So, but a view change is initiated only when there is a node crash.
Correct. When there is a change in the configuration of the system.
In some sense, then the primary or whoever is initiating the view change knows that and a particular.
Yeah, it knows it has crashed and it has come back from a crash. That's one of the reasons. So,
What it is not aware of is other nodes that have crashed.
yeah, the other nodes that have crashed, and it might, or other nodes have gone further ahead when it had crashed. That is the thing that it is trying to catch up on. That's what is happening. So, in phase 2, now we have defined a new view, that is, I am the primary, these are the backups, and we came to know that one backup was missing. Okay, so what do we need now? We need an extra node to participate in this algorithm, which is a witness node. So now the witness node gets the logs for this. The other interesting thing that, if you remember from the diagram that we had, was that the witness nodes did not have the entire file system. So now the witness nodes just keep logs. Okay, they just get the logs for this, so they can help with reconstruction of what happened from here onwards, where the witness nodes start participating in the algorithm. Right? So what has happened is that if a backup crashes, we have lost one of the n backups, so one copy of the file system is lost now. So when that backup comes back, that system comes back online, then what can happen is that I can pass the file system onto it and the copy can restart. But the system can function without that backup being online, meaning it is copying file system. So the copy of the file system happens without the NFS being down. Was I clear on that? So basically the backup which crashed could be brought back into sync with the rest of the system without bringing the system down. And the witness that got promoted can participate in the algorithm and the algorithm still works fine. Okay, so that's the kind of a beauty of this whole algorithm. I've kind of tried to simplify this a little bit, but it's a bit more complicated than that. There are a lot of other scenarios. Yeah.
But you just need one backup node to be.
Yeah, but the thing is that that is true. I mean,
You don't need all the n to be.
yeah, but we are trying to protect against n crashes. So basically, what we are saying here is that even if there are n crashes, I will still be able to serve and work. That's the only thing. So if our n is equal to 1, then your case, what you are saying is the case. Yes. Sir? Yes. Yeah. No, so there are three kinds of nodes: the primary, the backup, and witness. The witness comes into play only when one of the backup crashes.
All the backup crash.
No.
One of them is available, then we don't need the witness.
No, so why witness is needed? Sorry? Yeah, so basically you need, the bottom line is that the log needs to be, main memory log needs to be at n places for protecting against n crashes. That's the invariant kind of thing. Yes, backups will keep logs. So like you saw in the picture earlier, right? The backups had file system plus logs. No, the witness comes into play when a backup crashes. So one of the n backups crash and is not available to form the view. So then the primary will get a witness into the view to continue playing the algorithm. That's the idea. So as you can see, it's a kind of a involved thing, but at the same time it had some novel ideas at that time. So looking back at uh, this was one of the first implementations using conventional hardware, okay, which tried to give file system kind of the kinds of 4 good things that we talked about using cheap hardware, okay. And how did they do it? They tried to bring in that innovation from using the RAM, that is the main memory based mechanism, to store, give consistency without going to the disk, and the disk can be accessed in the background. So this was a very important kind of step towards building internet scale kind of systems. So this kind of became the basis to Google file system. So interestingly, that's the thing. And this work actually was done with Sanjay Ghemawat, who later wrote Google file system. So this is work done with Ghemawat and Liskov. So again, contribution here is, as you can see, it's a phenomenal this thing. The next one I wanted to talk about was a distributed operating system. It's about 3 o'clock. Tried to stop by 3:15, 3:20. So again, this is another algorithm which is a little heavy. So I was just wanting to ask the audience if should we go through this algorithm as well, or what do you guys think? Okay, cool. Let's give it a shot. If it becomes too heavy, then we can skip some of the things. Yeah, so there is T. So yeah, you have the bright light at the end of the tunnel, so to speak. There is T. Okay, so let's look at this interesting system. Again, when I looked at all of these systems, it was so interesting that Liskov contributed to some of the most phenomenal things that make the world today. So let's look at this one. So what did they try to do in Argus? Provide infrastructure for long-running applications. Okay, so they came up with this mechanism that there will be applications which will be running all the time, which was not the case at that time. Only there were lots of scientific computing that was going on this thing, but there were no applications per se which were running all the time. Today, for example, we have banking applications which run 24/7, which was not the case at that time. So they were trying to get infrastructure for this kind of a system. They were trying to give consistency and availability again in terms of failures and concurrency. Graceful degradation, this was again the common theme that was with HARP as well. And interestingly, the first they introduced was that the data access methods should be independent of the location. So what that meant was that things might move in this system. Okay, like it's a distributed system. I'm computing here, but something happens to this, and I want to move all this computation to another node. So my data access mechanism should be independent of which node I'm running on. Right? So these are the 4 goals of that. So they tried to implement this on something called as a shared nothing architecture. It's kind of very popular in parallel systems. A shared nothing architecture is basically a bunch of computers connected by a network, in simple words. So they have everything, the CPU, the memory, and the disk, everything is packaged. It just has a network connected to the other nodes. There can be shared disk architecture, for example, just comparing it, shared nothing. Shared disk is CPUs are here, memory is here, but all the writing happens to one disk. So that could be a network attached storage or something like that. So that's the shared disk architecture. There's also shared memory architectures. There are various kinds of parallel systems built there. In a shared nothing kind of architecture, systems are such that the application runs on different systems. So an application might consist of 10 things which are running on 10 nodes. Okay, so let's look at an interesting example here. Is distributed bank, like I was saying. So there can be front-end computers, right, which people are using to do operations. Then there is a back-end server which is running inside the branch. And then there are things that are like bigger systems which are tying all of this together. So what are the kinds of operations that you can do on this? There can be operations within the branch, within my computer, or across branches. So examples are like transactions across accounts. Account 1 is here, account 2 is there, so I want to transfer money. Or audit running across all branches. Things like that. So those are the various things. So this actually gives what was Argus trying to address, the kind of applications that they were trying to run on this system. So Argus primarily was all distributed object systems. Okay, everything was an object in the system, and all these objects were running at different nodes. One of the special objects was called as a guardian object. So guardian object is basically a bunch of code, and you look at it as a class which guards a resource. The resource could be something that is in a bank branch. A resource could be a device like printer, or resource could be an account. So account is a abstract resource, so we have it's protecting those things. Each of the guardians have a well-defined set of methods through which you can access them. So you cannot go beyond the methods. So it's basically encapsulation in that sense. So you call the methods on the guardian and you get your things done. So all components of a guardian reside on only one node. So that's an important point. Okay. Then the second point about guardian is that it contains a volatile part and a stable part. Okay. The stable part is the one that kind of is returned to disk periodically, and the volatile part gets reconstructed from this stable part later. So if you look at the fourth point there, guardians are basically a way to decompose your application into smaller parts. Okay, so you have a bigger application, you decompose it into smaller parts, this data and this computing. So for example, I could have an account as my data part of it, and the kinds of operations that I can do on this account, add money to it, deduct money to it from it, things like that. So this is a well kind of tied kind of data plus processing unit that I can put on one node. Okay, so basically it kind of forced the programmers to think about your application in terms of smaller parts and deploy those smaller parts to different nodes. The system also has special guardians which are like directory services, for example, or system services, naming service, things like those. Those are also implemented as guardians. So these are all the platform services that they provided. Then there is a concept called action. Okay, actions are basically computation parts, small computation things. The interesting properties of actions are that they are serializable and atomic. Okay, so when two actions work together, their effects that will be seen will be either one action after the other or the second action after the first one. So one order or the other, they are serializable. There will never be a mixture of the two together. And then they are atomic, that is either the entire action completes or nothing completes. Further, actions also have sub-actions. Okay, actions also have sub-actions. So let's, there is one other concept called atomic types. I'll explain this as well in a diagram. This is easier for people to understand. So let's take a quick top action here. Top action is, it is a big transaction that I want to do. Right? Here it says the top action is transfer 10 rupees from account A5 to A4, A3. Let's look at what happens next in Argus on this. So the next thing is that there are two sub-actions that get executed. Both of them could be executing in parallel. Okay, and what is that sub-action? They're trying to get the branch for each of these accounts. Which branch are these stored on? And to get the branch, they make calls to a system guardian, okay, called registry. So the registry somehow keeps list of banks to accounts mapping, right? When I call the guardian, I call it through what are called as handlers. Okay, so these are the concept of sub-action. Then the next sub-action, set of sub-action, is that I have to deduct 10 rupees from one of the accounts and add 10 rupees to another account. Now, this whole thing is part of an action. So that's why I was telling action are atomic. So if any of them fails, the whole action is aborted. So what basically Argus did was that they implemented distributed transactions. So you have point 1, point 2, point 3. Each of them could have action, sub-action kind of thing, right? And then you have the larger top action, which you can execute. And Argus provided you with a platform with executing this whole top action as one atomic operation. Okay, and then finally at the end there is what is called as two-phase commit. So if everybody is ready to commit, it commits this thing. So in a nutshell, this is what is Argus in some sense. Okay, so what they did was that they took this system and built a lot of interesting applications out of this. So this was went on for like 3-4 years, and eventually they came up with a platform with libraries and actually a programming language as well. So basically they took Clue, because Clue was Barbara's baby. They took Clue and then used it as extended it to build Argus. And actually it was running on, building a lot of complex applications were running on this mechanism, and it became pretty popular with the MIT community. They built, for example, a distributed document editing system was one of the thing that was built on this. So people from various MIT locations could sit down and edit one document together. It was an interesting this thing. So couple of interesting things about this. It did not have deadlock detection at that point of time. So people, suddenly it used to hang because there used to be a deadlock. Then people had to abort things or kill their jobs or whatever. So it was a user responsibility. So interesting, if I don't know if you noticed what the kinds of goals that we were having here. If you look at this, the overall thing, if you look back at Hadoop, for example, as today, the kinds of goals that Hadoop solves is very similar to what Argus did here. Okay, so conventional hardware, distributed system should degrade gracefully, as in if out of 10 servers, if 2 die, then 8 should still continue processing, but you will get lower throughput. So all of that is out here. Again, interesting thing is that a lot of ideas from Argus flowed into distributed systems like Hadoop. So looks like I had a crash here. It was not moving forward. Okay, so that was that. So that brings me to the light at the end of the tunnel, so to speak. So, yeah, please. Sure. Yeah, so example was this thing. In the long running system, if you look at a banking system as a long running system. So what do we need for long running systems? It's basically, even if even if it crashes, things should be able to join back after they come back online. And Argus provided for that. That is one. Second thing is that if there is a crash and there was a computation going on that, I should be able to take that computation and move it somewhere else. So like we were talking earlier, because the way it addresses data, meaning the file system mechanism to access data was independent of the location, you would, even if you move the data out and update your registry, the application would still run. So these two things made it kind of, if you look at systems at that time, they were not long running because of these two problems, right? So this system addressed that and allowed people to run a system which was kind of running for a long time. Does that answer your question?
So, so this needs some special kind of jobs, special kind of programs, which can be, let's say, broken into pieces and scheduled independently on each machine, right? So, for example, the transaction thing we said. So, if I have so it won't work for a application which is not designed to take benefit of this kind of distributed file system. For example, let's say a video game, so which is running on a single machine, but like I want to improve performance, so I cannot use this kind of thing to distribute it because it's not like cut into pieces which can run individually, right?
I agree. So basically, you cannot pick every application and make it distributed, right? But if you look at the goals of the system, right? So the goal was to provide for a platform and a language also. So it's like a distributed system plus language, okay, together put into one package so that you can build a bigger distributed system. So underneath there are some services that they provided. For example, the concept of guardian and actions. So things that were atomic. They had a lot of system services like registry and other things, which are kind of ahead of their time. You see today in distributed systems, these are some of the basic components that's what they built at that time. Any other questions?
Excuse me.
Yeah.
First of all, sorry, I'm sitting a bit too far.
That's okay. Yeah.
This was regarding to the 2n+1 architecture. In case of a crash,
Sure.
does the witness get promoted to a backup and start accepting data as well? One thing. Second thing, what happens in case of absence of witness, like n+1 architecture, with respect to redundancy? This is a twofold.
Okay, I'll come back to the second question in a bit, but let's look at the first one. So when one of the backups crash, okay, it crashes, then what happens is that if you look at this picture, one of those dark brown things is gone. So which means a copy of the file system is gone. Out of n, now we have n-1 copies of the file system, which is okay because I can still cater for n-1 crashes more. Okay, I have at least one copy of the file system. So consistency is maintained across crashes. But can I accept new update requests? To make sure that the new update requests are catered for, I need n copies of the log, which is the light brown colored thing there. Because one of the backups has crashed, I have lost one copy of the log now. So I replenish that one copy of the log from the witness. So the witness gets promoted. Yeah?
The assumption is that you can reconstruct data using the log, right?
Yes, of course. But
Surviving backup from the log.
So even if we get down to a situation of one backup and n-1 logs, you can still reconstruct the data using the log, right? if a crash happens.
Right. So we basically need to yeah, exactly. So I have one consistent point in the file system, which I know that is consistent on the file on the disk, and then a log which I can play on this file system to get the latest image of the file system. That's the assumption.
But then that log will be maintained post the crash, is it?
Yes, of course.
It will be maintained post the crash.
Correct.
So it will not be a complete log as such.
Yeah, it will not be complete log, because I know that in the other backups, they have the capability to make the file system consistent until the crash. In fact, they might be ahead of the crash as well. Right?
And what if there is no witnesses at all in terms of redundancy?
Yeah. So in terms of redundancy, like I said, if you need to cater for n crashes, then you need 2n+1 servers. If you don't have 2n+1 servers, then that means you will not be able to cater for so many crashes.
But if you maintain so many, n+1.
No, I didn't get your question though.
Suppose there are no witnesses at all.
Okay.
What happens in that scenario?
Yeah, so then what you have is
crash, right? See, if all the n witnesses have crashed, then none of the other backups can crash, because you have that is n crashes have already happened.
I have one main primary server and I have 4 backups.
and no witnesses at all, then the algorithm won't work in certain kinds of crashes, right?
No, but
Algorithm won't work. That's the basic
still
thing.
consistent. There is no problem.
So you can't give the guarantee of n crashes at any point of time.
So you need a backup and a witness for each.
So you cannot accept new updates, because if one of the
Because there are n backups, if all the n witnesses are crashed,
Yeah.
there are n backups. Each of the n backups have
correct, yeah, they can continue working, but then nothing can crash. Additional cannot crash. Yes, yes. Yeah, absolutely. Yeah. If the n witnesses crash, then it goes to this thing. We have reached the maximum. Yeah, absolutely.
N is the limit.
N is the limit. Yeah.
The purpose of the witness is just to make sure that the algorithm functions properly.
Exactly. Yeah. So interestingly, now that you mention it, how would you configure a bunch of file systems to be served by this? So the way I would configure this is, one server would act as the primary of one of the file systems, backup for another file system, and the witness on a third. So using a mechanism like this, I can cater to multiple file systems. So that's how you would reduce the load on this thing. The witness load comes in only when it is crashed. Right? So that's yeah. There's another question.
Could be a crash during view change as well.
Yes, absolutely. There could be a crash in the view change. Yeah. So that's an important point. There's again, there are lots of corner cases that this paper talks about, and they try to address each of them. But basically, the way I look at it, this is that if there's a view change going on, then we are trying to vote on who is the new primary and things like that, and there is a crash. Okay. So if it is in the first stage and I did not, there is a crash and I do not get sufficient amount of answers, then I will start choosing more witnesses. Right? If it is in the second stage, that is the second part of the two-phase commit, so in the second phase, then what happens is that the node actually had committed that it will take care of certain things, but then it is not able to. Then again another view change needs to happen. So if there is a crash, again that happens, then again we'll have to go through the view change, select. So primarily what happens, eventually what happens is another witness gets selected into the view, the overall view.
So whenever the primary node is updated, all the backups are sent, the respective information is sent. But we cannot say that all the backups remain in the same state at any point of time. So there may be different types of logs. All the backups have logs of different states, and witnesses contain only log. So what logs do the witnesses contain? Because each backup has a different set of log.
So
and
here is
the
the thing.
witnesses don't have their own data. So
Right.
whose data's log do they store?
Okay. So let me try to rephrase the question and see if I understand it correctly. So there is a crash and a witness has been introduced. Okay, the witness does not contain the file system, but they contain only logs. So one of the questions I heard there was that from what point onwards will they contain the logs? Okay, and that's a straightforward answer. That is,
I think the question was, will all witnesses have the same law?
Yeah.
I think they have to.
Because
Otherwise,
we cannot guarantee that at any point of time all the backups are in the same state.
No, they are.
While
if
one
they are not,
witness
then you
is-
cannot do anything.
Yeah.
And you don't have n+1 copies anyway.
Yeah, so which logs do the witnesses store?
It's all
Because
exactly
at
the
memory
same.
See,
state.
when we are talking about 2n+1, we are saying all 2n+1 are identical. If that is not guaranteed, then nothing will work.
Then what is the need for GLB?
The GLB guarantees actually that when the GLB is marked, it means it is everyone is unsafe.
That's the point at which it is guaranteed.
Yes.
Others may be also writing some other stuff.
That is the point beyond which you cannot guarantee. So that's the point.
So when something, one of the node gets crashed, the jailbait doesn't get updated.
Correct.
Yes.
no, one of the node crashes, yes, you're right. A view change starts, which means I stop accepting any more new this thing. The top will not grow in this picture. Okay. The GLB will also not get updated because I wouldn't get new these things from that node, right, which has crashed. All the other people would have written today, but that one node which has crashed has not. So I do this view change algorithm and come back to state again, and then the GLB starts updating.
Yeah, sure. I am trying to understand the CAP theorem. So, would it be applicable here? I am not able to see that. Can you help me with that?
Which theorem is that?
CAP theorem.
I am not sure what that theorem is.
Brewer's conjecture, which was later proved as a theorem. Consistency, availability, and partitioning in a distributed system.
Okay.
All three of these cannot be obtained simultaneously.
No, I'm sorry, I'm not sure. I understand the. So maybe we can have a discussion after this. Okay, so let's come back to the conclusion part. We just rush to this. So what I was talking about, Barbara, just reiterating what she has done in this whole this thing. First of all, a superwoman, according to what I was saying, the first lady to get a PhD. She has contributed to things like object-oriented stuff, distributed systems. So one of the common themes in all her contributions is that they became common sense after a decade or so. So which actually says that she was so far ahead and she was hitting the right spots that she knew that these are going to be the norm down the line. And if you look at her research today, she is working in privacy of sensitive data like credit cards and things like that. I'm pretty sure she'll come up with something interesting which will become common sense or the norm in like 10-15 years. So I'll wait to see what those will be. Another side comment is some of her best papers are non-mathematical in nature and I could understand them pretty easily. Just to kind of leave the this thing, here is what she says to young engineers. I thought there's going to be a lot of programmers on this forum. So I thought when I look back at my early career, one of the things that strikes is the randomness of the process in which things happen. That's what she says. So she went into computer science by accident. All she was doing was responding to obstacles and opportunities, what she says. But the interesting thing is that she found her passion and then realized that she was really committed to give to her passion. And interestingly, the last thing she says is that when you know your passion, you need to also be ready to change your goals in life to move towards your passion. So pretty interesting and very, very strong this thing. Actually, I would suggest that people read the entire write-up she has done on that website, engineeringgirl.org. it's a very touching and pretty inspiring stuff. So with that, folks, I'll